In this video, we explain how the exponential function is defined. At least we give one way to define it. There are several equivalent ways, but this approach is naturally motivated by a question of compound interest. Now imagine your money sitting in a bank account and accumulating interest over time. In order to make the final connection, we'll need L'Hopital's rule. So this will be a continuation of our previous video on L'Hopital's rule. There I discussed several indeterminate forms, but my table of indeterminate forms in that video was far from complete, and I left out some interesting ones just because the video was getting too long. And this one, however, is too important to leave out, and it deserves an entire video by itself, which is what I'm doing here. So imagine that you deposit $1,000 in a bank account on the first day of the year. This account pays interest at an annual rate of 6%. For simplicity, we'll assume that interest is compounded annually, which means all your interest is paid at the end of the year. The interest after a year is 6% of your initial amount. Just multiply the interest rate times your original deposit. In our example, after a year, we have the original deposit plus $60 interest. That's $1,060 altogether. Notice that our balance was multiplied by 1 plus R, 1 plus the interest rate, to get the new balance. Now let's change the example slightly. We'll keep the same nominal interest rate of 6%, but let's compound the interest semi-annually, and that means every 6 months. That means after 6 months, half of your annual interest is paid. That's just 3% of $1,000. So your new balance at the end of July is $1,030. After another 6 months, you again earn 3% interest, but this time based on the balance from the end of July. So you add 3% of $1,030, and that's $30.90. So at the end of the year, you actually have $1,060 plus 90 cents, just a little bit more than the previous scenario, because this time you're earning interest also on your interest. So notice in this scenario, every 6 months your balance is multiplied by 1.03. That's good. So let's do better. Let's compound our interest quarterly. This means every 3 months you get quarterly interest payment of 1.5%, a quarter of the annual rate. So every 3 months your balance is multiplied by 1.015. After a year, your balance is multiplied by 1.015 4 times. And the balance is therefore, over 4 interest periods, is $1,061.36. Notice is a little bit better than the previous. It's actually 46 cents better than semi-annual compounded interest. So let's try compounding interest monthly. Every month we earn 0.5% interest. That's the annual rate divided by 12. So every month our balance is multiplied by 1.005. And after a year, our balance is multiplied by 1.005 to the 12th. Our year-end balance is now $1,061.68. Again, a slight improvement of 32 cents over the quarterly compounded interest. Okay, so I'm going to do one more incremental improvement before going for the punchline. This time we're going to compound the interest every day. Every day our balance is multiplied by this factor I'm showing you here. And after 365 days of a year, our year-end balance is $1,061.83, which again is a slight improvement. It's actually 17 cents better than the previous. Clearly, the more often interest is compounded, the better for the customer. But the gains are starting to get incremental. If you compound the interest every minute or every second, every microsecond, that's going to be such a slight improvement. It's not going to make you a millionaire. There's a limit to how much you can improve your balance by compounding more often. That limit is known as continuously compounded interest. So for this, we'll start just as before, same setup. If interest is compounded n times per year, then at the end of a year we have n interest periods, and our balance has been multiplied by this factor, 1 plus r over n to the power n. For continuously compounded interest, we let n go to infinity. The limit, as I'll explain, is found by multiplying by e to the r. In our example, that means a year-end balance of $1,061.84. Okay, so you can see it's just 1 cent better than compounding every day. And so I'll work out this limit for you. You can see how the exponential function is getting in here. It's the natural base of exponential, the base e, which is 2.7182818, ... So this gives a good explanation why e is important and why it's natural. It is like the gold standard of all exponentials and all logarithms. Every other base of exponential and logarithm is understood based on this gold standard. So I'm not just speaking gold standard financially, but mathematically as well. So I've introduced one way of defining the exponential function as this limit shown here on the top. In our context, n was a whole number, an integer, because it was the number of interest periods. But I'm going to replace n by a variable x, which can be any positive number, and then it'll look more like the kind of limits we've been talking about in our course. Keep in mind here that r is a constant, but r can be any constant number. It can be positive, negative, or 0. For this, it doesn't matter. The limit has an indeterminate form. You see, the base, 1 plus r over x, goes to 1 as x goes to infinity. The base is going to 1. So 1 to any power is 1, right? So that tends to pull the expression down to 1. However, the exponent x is going to infinity, and that tends to raise the expression up towards infinity. So it's this competition between irresistible forces, and the question is always which one wins. Is the limit 1, or is it infinity, or maybe something in between, or does the limit even exist at all? All these outcomes are conceivable when you have an indeterminate form. Now you can use L'Hopital's rule to resolve what the actual limit is, but first you'll need to rewrite the expression, since our expression doesn't have a quotient form that's needed for L'Hopital's rule. So to do that, I'm going to make this change a variable. First of all, again, let x be r over u minus 1. Solve for u. U is 1 plus r over x. Notice that since x is going to infinity, that makes u go to 1. So I can rewrite this as a limit as u goes to 1, and the expression gets rewritten this way as a power of u. And it's not quite a quotient yet, but for that, let's use our rules for exponentials and logarithms, like I've shown you here. And now I'm taking the limit of e to some power, and inside that exponent you see a quotient, and that's what we're going for. This thing that I've identified, I've highlighted, is an indeterminate form 0 over 0. Natural log of u is going to 0. The denominator, u minus 1, is also going to 0. So this is an indeterminate form 0 over 0 that I can apply L'Hopital's rule. So for now, just forget about the exponential part outside. Just focus on this thing inside, which is a quotient in the right form that we need. For that, as I've highlighted on the bottom of the page, on the bottom of the slide, take the derivative top and bottom, use L'Hopital's rule, and get a limit of 1. just for the inside part. And now I substitute that in, and I get e to the r for my overall limit. That's the answer that I was looking for. I said the answer would be e to the r. So you'll notice that I effectively moved the limit inside the exponential. I took the limit of the exponential by taking the exponential of the limit. I just changed the order, right? And can I do that? So can I move the limit inside my function, my exponential? And, well, yes, I can do that because of the continuity of the exponential function. Moving limits inside is something you can only do when the function is continuous. That's what continuity is actually all about. That's why we need it. For a discontinuous function, you cannot move the limit inside like we just did. Now, there are, in fact, several ways you can define the constant e, or the exponential function e to the x. But however you do it, you'll see that e, or e to the x, are natural and they're universal things. In our textbook that we used for my course here, we used a different approach to get at the constant e by considering all exponential graphs a to the x. And they all go through the same y-intercept at 1, but they go through that intercept with different slopes, and we identified by continuity that there should be some particular choice of the base a for which that slope is 1. And that's how we got our base e. And from this, it follows that the derivative of e to the x is e to the x, and all the good properties that we want. That approach, however, begs the question of what e to the x even means, how it's defined, or how is a to the x defined. This approach that I'm showing you here gives you access to that. It actually shows you how you can define e to any power.